Welcome to another exciting episode of the Organic Chemistry course. So, today our discussion is on organic nitrogen compounds. So, our first subheading there is the formation of ethylamine by nitrile reduction. So, I would like to call your attention to the video I did under halogen derivatives. How nitriles are formed, right? The reactions which we said result in an increase in the number of carbon atoms in a chain, okay? So these nitriles are reduced. When we're talking about reduction, most of the time we're adding hydrogen, right? That's what it is, right? Adding hydrogen using the following mediums, using the following reagents: sodium borohydride in dry ether is a reducing agent, okay? And also lithium aluminium hydride in dry ether, or hydrogen of a nickel catalyst at 150 degrees Celsius and 4 atmospheres. Okay, that's what there is to it. Then this leads to the formation of what? Of ethylamine. The carbon, this carbon atom here receives two hydrogens, two hydrogens, and this nitrogen also receives two hydrogens. That's what there is to it, right? Now let's just move on to the next subheading there that we have here. The formation of phenylamine, which is this one, right? By the reduction of nitrobenzene. Reduction, what we're doing, we're just adding hydrogen, right? In the presence of a tin catalyst, in the presence of sulfuric acid under reflux conditions to produce our phenylamine and water, right? Phenylamine is alkaline, it's a base, okay? So it reacts with acids like HCl to produce a salt, right? Like in this case, this is phenylamine, our acid plus our base plus our acid HCl to produce our salt. The salt structure is got an NH3 there. It's NH3 plus and the chloride negative ion there. That's the structure or formula for our salt. So that salt now, when you add a base to that salt, it goes back to form phenylamine, water, and chloride ions. That's all. Now, as far as this topic is concerned, we come to the most important aspect of this topic, the basicity of amines. What is it that makes amines basic? Okay, amines have got a nitrogen atom, right? Amines have got a nitrogen atom. And that nitrogen atom is a lone pair of electrons which readily accept a proton. So the more readily available that lone pair of electron is to protons, the more basic the amine. So this is just a typical example to show how this base here is accepting this proton to form this positively charged compound, okay? So phenylamine being a base, when it reacts with water, it releases hydroxyl ions in solution, right? Phenylamine also being basic reacts with hydrochloric acid, right, according to this equation to form our salt. I think this is just a repetition of what I've just touched on above there, right? Now, I want to move on to a very most important heading here, the relative basicity of amines. I need to explain a few things here. We've got three molecules here, A, B, and C, all of which are amines. And all these amines have a nitrogen atom which has a lone pair of electrons readily available for proton acceptance. Okay, all of them have got this nitrogen atom with a lone pair of electrons that is available for proton acceptance. Now, B is said to be the most basic of these three compounds. Why? Because it has two alkyl groups, right? One of which is this one, 1, 2. These alkyl groups tend to push electrons towards the nitrogen atom, right? Making the nitrogen atom electron rich. They enhance the electron density of the nitrogen atom, making the lone pair of electrons on the nitrogen atom readily available for proton acceptance. Right? Now, molecule C, on the other hand, should have been the most basic of these three compounds because of the three alkyl groups, but is not due to a phenomena that is known as steric hindrance. Before the proton can accept the lone pair of electrons, it will face some hindrances or bombardments from the alkyl groups, from these alkyl groups that are surrounding the nitrogen atom. That's why this molecule C is the second most alkaline molecule. Okay, now A now is the second most basic, is the third most basic, because it has just only one group to push electrons towards the nitrogen atom. That's all there is to it. You do well to follow my examples there, because the examples that I have covered here are the ones that are mostly asked in your Cambridge AS and A2 exams. So just make sure you go through this video over and over until you get it. Okay, now moving on to the relative basicities of ammonia NH3, ethylamine, and ethenamide and phenylamine. Right? Of these four molecules, number 2 is the most basic. Right? Number 2 is the most basic because it is an alkyl group which pushes electrons. It is an alkyl group which pushes electrons towards the nitrogen atom, causing the lone pair of electrons on the nitrogen atom to be readily available for proton acceptance. Okay. Now, the second most basic of these four compounds is ammonia. Because its lone pair of electrons is just readily available for proton acceptance. Now, why is number 4 here the third most basic? Because remember, phenylamine NH2, if you revisit my topic entitled hydrocarbons, I referred to this NH2 group as an activator. It gives electrons to the benzene ring, right? Since it gives electrons to the benzene ring, the nitrogen atom there is electron deficient. Therefore, its lone pair of electrons is not readily available for proton acceptance. Okay, I have this page reproduced here. It's the same page as this one. It's the same page, right? Now, when it comes to the amide, now when it comes to the amide, now what about this one? This amide. Amides are neutral. They're generally neutral. Okay, amides are neutral. So I gave you a simple point. Since it is neutral, it is the least basic of those four compounds. In simple terms, it can be said that 3 is neutral, which is the amide, because the lone pair of electrons on the nitrogen atom is delocalized over the amide bond. That's all there is to it. That's all you need to say, right, to make a good impression on this one. Moving on, the reactions of phenylamine or aniline with bromine. Phenylamine reacts with bromine, aqueous bromine, to produce a white compound or a white precipitate known as 2,4,6-tribromophenylamine. This one, right? In this reaction, bromine is decolorized, right? You must also understand that this reaction is also used to test for phenylamine, right? Now, there is a point there that I wrote there, a nice to know statement, which says that phenol can also be tested by adding FeCO3, iron 3 chloride, and a violet precipitate is formed if phenol is present. I could have done this earlier when I was talking about the chemistry of phenol, but I decided to put it here for some very important psychological reason. Okay, so just stick with me. I'll make a point. Okay, this was just the previous page we were talking about reproduced. Okay, so the next topic that we're covering is this one. So the reactions of phenylamine with nitrous acid. Nitrous acid is HNO2. HNO2. So nitrous acid now is unstable. Nitrous acid is unstable. So in this reaction, we use sodium nitrite and HCl. Like in this reaction here, reaction 1, you add sodium to sodium and nitrite, here you add HCl, and you produce your what? Your unstable acid, nitrous acid plus sodium chloride. What then happens? In excess acid, in excess hydrochloric acid, this nitrous acid reacts with what? Hydrochloric acid and phenylamine below 10 degrees Celsius to produce a diazonium salt, H2O and chloride ion. Other versions, right? Other versions combine these two to produce something like this. N2 plus CO negative, right? It's the same thing, guys. It's the same thing. Okay? So you're also supposed to understand, what you're also supposed to understand is that this reaction is reaction mechanism number 2. By adding the two equations above, 1 and 2, this was my 1 and this is my 2, right? You obtain an overall reaction for what is happening. So this reaction tells it all, right? Tells it all that for you to produce this diazonium salt from phenylamine, you need these two reagents, nitrous acid and hydrochloric acid. These two are the same. These two are the same as just saying what? HNO2, nitrous acid, is the same thing, okay? Any temperature now, this point, guys, is very, very important. It's a nice to know statement. Any temperature above 10 degrees Celsius would cause the diazonium salt to decompose into its nitrogen, phenol, and water. That's all there is to it. You should know this statement, guys, okay? The more you think and revisit this video and read these notes, you'll be the better for it. I recommend that you do, okay? Let's move on. The diazonium ion formed in this reaction, in the above stage, okay, can be reacted with phenol in what is called a diazotization reaction. A diazotization reaction. So what happens here? One hydrogen atom, looking at phenol. Remember from our topic of hydrocarbons, the OH group in phenol is an activator. It activates these positions for substitution. So either of these three positions can be substituted, right? The hydrogens there can be substituted, and this nitrogen here forms a bond there, and the hydrogen is ejected here. That's why I wrote at the bottom there to say, take note of the 2,4 directing effect of the OH group on the benzene ring. Okay? So I really try to think around how this was formed, okay? There was a hydrogen atom that was here, it was replaced, right, by this N2 bond, by this N2 structure. Then this positive charge was taken by the hydrogen here on the other side. That's all. Okay? So this is a coupling reaction or electrophilic substitution. Okay? In these reactions, colored compounds are produced, which are called azo compounds. They are used to make dyes. So there are also other nice to know statements that are very, very important that I pointed out in these notes, okay? To say when primary amines are reacted with nitrous acid here, effervescence is observed, right? Because nitrogen gas is being produced under such circumstances, right? Another case is that of secondary amines reacting with nitrous acid. A yellow oily layer is observed. Right? A yellow oily layer is observed. These are just nice to know statements, guys. Just know them, okay? They will come in handy, I'm sure. So diazotization reactions and coupling reactions are used to make dyes. This is just a repetition, a re-emphasis of what I've been trying to say, okay? Now let us talk about the formation of amides, right? The formation of amides. Primary amines react with acyl chlorides, and in this reaction an amide is produced. This with the peptide linkage, okay? Or an amide bond, an amide linkage. Another way of performing an amide is taking ammonia NH3 plus an acyl chloride. That can also produce your amide linkage and HCl. You should try it, okay? Another point that you were supposed to know is the shape of your amides. To say amides are planar, that planar in shape. Okay, they are planar in shape. Look at this nitrogen atom. It is surrounded by 3 regions of negative charge in a planar shape, right? Look at this carbon atom that we have here. It is surrounded by 3 regions of negative charge, right? In a planar like shape. So the shape of this amide bond is planar. It's just general knowledge, okay? You just know that, okay? Now let us talk about the amide hydrolysis. Amides can be hydrolyzed by heating them with sodium aqueous sodium hydroxide or dilute acid, right? Or dilute acid. Look, here's our amide. By adding in acid, you produce your carboxylic acid and your ethylamine, right? By heating your amide with a base hydrolysis, you produce your amine plus your carboxylate salt, right? So there's just take a piece of paper and just write some of the formulas here that help you summarize what has been happening there. So base hydrolysis here, base hydrolysis is equals to acid salt plus primary amine. Acid hydrolysis means different color. Acid hydrolysis equals to acid plus primary what? Amine. That's all. Now I want to move on to another a very important subject of amino acids. All amino acids have this structure. All amino acids have this structure that you see there. They have this NH2 group, which is alkaline, and this COOH group that is acidic. All amino acids just differ in the other group. That's all. That's why they only differ. So because of the amine side, they are said to be basic, and because of the carboxyl side, they are said to be acidic, right? Amino acids have acidic and basic properties. Therefore, they are said to be amphoteric. They are said to be amphoteric, okay? Let's move on and I'll show you. So here's an example of an amino acid acting as a base. When an amino acid acts as a base, what does it do? It accepts a proton. So it takes a proton from water to be accepted by this what? By the nitrogen there, to form an NH3 plus kind of structure plus an OH negative bond here. Okay? And in the next subheading there, we have amino acids reacting as acids. What do? They donate a proton. This proton on the acid group is given to the water. Water is protonated, right, to form your carboxylate salt and your H plus ion. This same as saying H plus. Now you must also see that these are reversible reactions, showing that the amino acids are weak acids, right? They are weak acids and bases, so they partially dissociate in water. And there's another very important phenomena. I shall do a separate video on this, on Zwitter ions, right? The isoelectric point, okay? I shall talk about that. Amino acids can undergo self-protonation. Amino acids can undergo self-protonation. In other words, the acid part of the carboxylic acid can lose a proton, and the alkaline side of the carboxylic acid receives that proton to form what is called a Zwitter ion. Alright? You're going to find out that you're going to find more of these Zwitter ions when you're now doing the study of what is called electrophoresis. But not in this video, okay? Not on this video. So this is Zwitter ion, a doubly oppositely charged species. That is the Zwitter ion. It's positively charged this side, which is positive, and this side which is negative. So that's what you're just supposed to know. But I'm going to make a separate video, right, on electrophoresis, where I'm going to talk more about these Zwitter ions, okay? Very interesting topic. It will be supplementary to this topic, okay? Okay, let's move on. So what you're supposed just to understand and know is that proteins are crystalline solids with high melting points, and these are usually solids and they have high solubilities in water. That's all. Right? Now, in the next subheading there, you are shown two amino acids coming together. Yeah, this type of reaction is a condensation reaction. It's a condensation reaction. Condensation. It's a condensation reaction. In my polymerization video, I'm going to touch more about this concept of condensation. But two amino acid molecules can come together to form a new molecule through the elimination of water to form a peptide linkage or an amide linkage, right? When amino acids are joined together, they form a peptide linkages, right? They form peptide linkages. That's all you're supposed to know, right? And now, as I close, I want to talk about the hydrolysis of proteins. Proteins are hydrolyzed into amino acids when they are heated in the presence of a base or an acid. I think we've covered this. This is just a re-emphasis, right? So when you're adding H2O there, it's like acid hydrolysis. You've just formed your carboxylic acid and your primary amine. That's all there is to it. Okay? That's all there is to it. So this brings us to the end of the nitrogen compounds episode. I hope you found this video helpful. And if you did and would like to support the channel, please comment, like and subscribe. And I'll see you all next time. Take care.